Loud. Welcome to the Monday seminar, folks. It's really wonderful to see you all. We've been off for a couple weeks for holiday and then also the EGU meeting in Vienna. But I'm super excited that Whitney Behr is with us today from ETH. As I think you know, the formal part of the introduction happens by email, and I guess I hope you're all on that list so you could read about the stellar academic background of Whitney Behr and various things that she's done. But today we are going to hear, as you see from this title, about subduction zone deformation. I will remind you that our normal mode of operation is to ask people to mute themselves, but to encourage you to unmute, to ask points of clarification, and to help Whitney remember that she's not just talking to her computer screen, which is one of the things that happens. The downside, of course, is exactly that. And the upside is that we have an extended period of discussion. Whitney's agreed to stay with us until a half an hour or so after what will probably be about an hour-long talk. And typically, that's quite a nice time for a discussion and question and answer period led by Whitney. So I just encourage everybody to be prepared to engage in that and to be involved in that. And especially early career people, grad students, it's an opportunity to interact with experts about something. So please make yourself ready to take advantage of that. I don't have anything else to say. I will turn things over to Whitney. I'll thank her very much for organizing the talk and look forward to hear what she has to tell us. So all yours, Whitney. Thank you.
Cool. Yeah, thanks, Chris. Thanks for the introduction and also for the invitation. I've heard a lot about this series and it's exciting to be here and I look forward to the discussion. So my talk today focuses on constraints that we can use from exhumed rocks on the sort of nature and processes occurring along the subduction interface in the deep slow slip and tremor source region. And I'll be doing my best to sort of compare and contrast observations from geophysical constraints on slow slip and modern subduction zones to features that we see in rocks. And I'll be focusing a lot on one of my favorite places to work, the beautiful island of Syros in the Cyclades in Greece. And this work's been ongoing in my group for several years now. Some of you have seen components of this talk probably over the years and have been kind of adding to it from the work that they've done. Several wonderful former and current students, postdocs, and colleagues, all of which are listed here. And it's been funded for the last several years by an ERC starting grant that I received in 2020, along with several internal sources from ETH. Okay, so I think most people in this audience are probably familiar with slow slip, but just in case there's students or researchers in adjacent field, I wanted to just give a quick overview of what it actually is. So as the name implies, slow slip and tremor consist of two distinct components. The slow slip part, which is detected with geodetic methods, represents aseismic slip events that can have quite large displacements, often equivalent to magnitude 5 or greater, 6 or 7 earthquakes. But rather than accumulating that slip over seconds to minutes, like typical earthquakes, slow slip occurs over days to months, sometimes even years. And then the tremor component refers to seismically detected very low frequency and low frequency earthquakes, usually in the same regions or activated at similar times as the slow slip events, but these occur on timescales of seconds to hours. And these tend to occur together. Sometimes they're referred to as slow slip and tremor, sometimes ETS, episodic tremor and slip. And this interesting mode of fault slip and subduction zones tends to sort of bookend the seismogenic locked section of the megathrust. So it occurs at both shallow conditions near the trench in some places, as well as deep conditions at and around the mantle wedge corner below the seismogenic place where we expect regular megathrust earthquakes. And this mode of fault slip was first recognized in Cascadia in the early 2000s, but these types of events have now been detected at many plate boundaries worldwide for a wide range of subduction zones with different thermal gradients. The orange ribbons on this map shows most of the regions where SSC phenomena have been detected so far. They tend to cluster along the Pacific Ring of Fire and mostly in subduction zones, but also on some parts of the San Andreas Fault. And then the diagram on the right shows the thermal gradients for many of these subduction zones, which are quite variable from cold in places like New Zealand to relatively warm in Mexico and Cascadia. And the general depth of deep slow slip and tremor, which I'll be focusing on today, tends to be from about 25 to 55 kilometers in these regions. So if you think about this in terms of metamorphic conditions, this spans blue schist, eclogite, and even in warmer cases, amphibolite facies conditions. And ever since people have discovered them, they've been wondering sort of what they mean, wondering what it is in terms of the rock types, the fluid flow conditions, the metamorphic conditions, or the reactions that are taking place, the deformation mechanisms that explain these different transient signals occurring as a function of depth and plate boundary faults, and explain why they behave through slow aseismic slip with tremor as opposed to either purely aseismic slip or fast seismic slip. And so what I want to do today is briefly summarize some of the constraints we have from geophysics on the deep slow slip and tremor source region, and I'll focus on some of the aspects that I'll later kind of hark back to that because they're potentially scalable or relevant to observations that we can make from the geologic record. And then I'll switch to, for most of the talk, to talk about what the rocks tell us and speculate on what some of the features that we see in the rocks might correspond to in the geophysical record for modern subduction zones, with those examples coming from Syros Island. And then I'll finish up with highlighting a couple of the many remaining questions, the ones that are kind of near and dear to my heart at this point, that I think are still pending. So a little more detail on the environment of slow slip. So this is a cross-section through the slow slip source region in Tokai in Japan. As I already noted, deep slow slip tends to occur down dip of the locked megathrust near the mantle wedge quarter. And when we look at the geophysical properties in these regions, we commonly see low seismic velocities, as in the red curve here, and high VP-VS ratios, as in the blue. And this is interpreted to reflect regions of both high fluid content and high fluid pressures, where the fluids are likely derived from vigorous sort of metamorphic reactions, such as crustal eclogitization. And then the fluid pressures are produced due to some form of transient sealing in the subduction interface or along the sort of subduction interface for our contact. These relationships of paired high VPVS and low seismic velocities are observed in many other subduction zones as well, not just here in Japan. So then looking a bit at some of the spatiotemporal characteristics. So this is a plot for Cascadia from Michel and others, time on the x-axis and latitude on the y-axis. And it's showing the time series of the long strike distribution of both low frequency earthquakes. So those are the black dots, and then slow slip events, which are regions colored by slip rate. And a couple of things to notice. Firstly, the LFEs define these sort of streaks or lineaments in the along strike direction. These light up repeatedly over time, kind of the same general regions seem to be lighting up throughout the time series. And they recur really rapidly. So on essentially a daily or weekly basis, you're getting these repetitions of these lineaments sort of firing off tremor events over and over again. And in many places, they're not accompanied at all by slow slips, or they're kind of just background deformation. And then secondly, the slow slip events also define these along strike streaks that seem to be kind of persistent and repeating over time. But you can see that their recurrence intervals are much longer, more on the order of months or multiple months. And they pretty much always do overlap with or are accompanied by low frequency earthquakes. So that's kind of the largest scale showing the along strike variations at large scale for Cascadia. Now, if we zoom in also on Cascadia and just look at the LFE distributions, here we see they also show a kind of streaking pattern zoomed in, but in this case, these are oriented in the down dip direction toward the northeast rather than along strike. And we can actually trace those same sort of streaks that are lighting up in 2003 through to the year 2004, again, suggesting the kind of persistent heterogeneities or lineaments being defined by the tremor here. And then finally, we can zoom in at the scale of tens of kilometers, and we see that individual LFEs define small patches or families that are now 1 to 2 kilometers in length or width. So individuals or little clusters here can now be defined as little patches that are on the kilometer scale. So these studies illustrate that there's kind of a hierarchy of spatial distribution or persistent heterogeneities, and they're defined at the minimum length scale of a kilometer or so, but that ultimately these have to kind of connect up to produce the largest multi-kilometric length scale associated with magnitude 5 and above slow slip events. So the third thing I want to highlight from the geophysical record is the spatial patterns of tremor migration, and these have been interpreted as evidence that slow slip and tremor is accompanied by fairly rapid fluid or fluid pressure migration. So this is an example now from Guerrero in Mexico, from Frank and others, and this figure shows time on the x-axis, and then each of the colored curves represents low frequency earthquake counts for different down dip levels of the interface, with red being the deepest part of the interface and then blue being the shallowest. And this time series is recorded across a slow slip event that occurred from April to November in 2006. And what it shows is that at the start of the 2006 slow slip event, LFE counts rise all along the interface from shallow to deep. But then about halfway through the slow slip events, those LFE counts start to drop, first at the deepest levels and then progressively shallower until the end of the slow slip event. And this was interpreted as in this cartoon, where at the start of the slow slip event, pore fluid pressures are high enough to generate sort of failure from the transient zone to what's labeled this kind of sweet spot. This triggers an acceleration in low frequency earthquakes all across the slow slip zone. And this is interpreted in this paper as a sort of breaching of the upper plate seal and transient increases in permeability all along the interface. But then as the slow slip event propagates, the fluid pressure is sort of interpreted to progressively drop, first at the deepest levels and then gradually towards shallower levels. So there's this kind of migration of a fluid pressure pulse from the sweet spot back to the transient zone. And the rate of that migration is about 1 kilometer per day. And in several studies, including this one, they assume that that rate reflects some sort of fluid or fluid pressure diffusion process. And that allows you to use a diffusion equation to estimate the permeability based on the diffusion coefficient and some assumptions about porosity and fluid viscosity and storage coefficient. And the value that they come up with there is estimates about 10 to the minus 12 meters squared. And several other people have used these kind of tremor migration rates to estimate permeability in a similar way. And those are generally in this same range of 10 to the minus 12 meters squared, although of course the uncertainties are probably on the order of 1 to 2 orders of magnitude. But the main point here that I'll come back to later is that this is a really high transient permeability for what we expect for deep-seated rocks. So based on observations like those that I just highlighted, the view from geophysics, you've probably seen a diagram like this before. It's developed, it's sort of shown schematically here. There's this general concept of a heterogeneous fault plane where the locked part of the megathrust probably hosts really large asperities, tens to hundreds of kilometers in dimension. But then down dip, these asperities are kind of smaller and fewer, maybe on the order of kilometers, and they define these sort of patches or streaks both along strike and down dip. And the low velocity and the high VP-VS ratios estimated from those seismological observations suggest the presence of this very fluid-rich and high fluid pressure environment. And then the combined seismological and geodetic data highlight these two different spatiotemporal event patterns, LFEs representing thousands of kilometer scale, seismically detectable events that recur daily, and then slow slip, which are these really large aseismic geodetically detected events recurring over months. And then the slow slip events are associated with sort of spatial migration of tremor, and that's interpreted to reflect high transient permeabilities on the order of 10 to the minus 12. So now I want to switch gears to discuss what sort of corresponding types of information we can get from studying the exhumed rock record. And so we can try to translate some of these observations to corresponding questions for geologists. So For example, when it comes to heterogeneities, we can ask, well, what types and length scales of heterogeneities are actually preserved in the rock record? When it comes to observations of transient events such as LFEs and slow slip, we can ask what types of transient deformation features do we actually see in exhumed rocks? And then when it comes to evidence for rapid fluid migration, we can ask what the plumbing systems of subduction shear zones look like. And in some cases, as I'll show later, we can try to quantify both the background and transient permeability that might define these slow slip host regions. So the way that we get at this is by studying exhumed subduction complexes that have been brought to the surface through later tectonic processes. These are fairly globally distributed in orogenic regions. I've shown them here as blue lines. These are representing accretionary complexes in which blue schist and eclogites are preserved. And the processes by which these are sort of assembled and then exhumed to the surface can be quite complex and can vary from region to region, but in a simplified way, in general, these subduction complexes all characteristically involve a process referred to as tectonic underplating, which is a form of accretion where fragments of the downgoing slab become sliced off along the megathrust shear zone segments and then attached to the upper plate. So this is especially common in the deeper parts of accretionary margins as opposed to the shallower parts where they're off-scraped. This is an example from numerical models from Jonas Rue's paper. And you can see how these slices of oceanic crust and mantle and metasediments can be sort of slivered off. And the active subduction interface, therefore, kind of steps progressively downward with time from one rheologically weak material to another structurally deeper one. And many different rock types become sort of juxtaposed in this environment, including sediments, mafic oceanic crust, slivers of partially serpentinized mantle. And oftentimes these slivers are then partially exhumed back to the surface along the top of the subducting slab during ongoing subduction and afterward. And that's how we could study them at the surface, this kind of assembly, accretionary assembly at the surface. So the particular subduction complex I'll be focusing on today is the spectacular cycladic blue schist unit in the southern Aegean. It's part of the currently active Aegean subduction zone, which has been accommodating convergence between the African and the Aegean sea plate since the late Cretaceous. And through time, the slab has continuously sort of rolled back toward the south, generating magmatism and inducing extension in its wake. And that extension has exhumed the older, previously subducted and accreted material, and that's now nicely exposed on the Cycladic islands. So if we zoom in on the Cyclades located here, the cycladic blue schist unit, I'll refer to it as the CBU. In this region, it records subduction and exhumation of both oceanic and continental fragments starting in the Eocene. The subducted related rocks were initially exhumed along the top of the subducting slab under relatively cold conditions, and then later they were captured from middle crust to the surface by detachment faults in the early to mid Miocene. So these are the north, south, and west cycladic detachments shown in white here. Syros Island, shown in the yellow box right in the middle of this kind of island core complex, represents one of the structurally deepest and the best preserved exposures of the CBU. So it has beautiful preservation of blue schist to eclogite facies metamorphism in both oceanic and continental affinity subducted slices. And I'll be showing examples from various parts of the islands, but especially from regions that preserve features more representative of oceanic materials that are reasonable analogs for Pacific style subduction. In terms of PT conditions of rocks on Syros, they record conditions similar to warm subduction zones like Cascadia in Mexico. The peak metamorphism is estimated around 15 to 16 kilobars, and the early exhumation, sort of along the top of the slab when this was at 4-arc conditions, is constrained to about 12 to 14 kilobars. So both of these conditions overlap with the general depth of slow slip phenomena in warm subduction zones. So I'm especially going to highlight this area in northern Syros known as the compost belts, which is where we've been working most recently. And it's a thrust dense shear zone that records north-directed subduction of a small ocean basin. And it's one of these areas that really nicely preserves peak or near peak conditions with relatively little to no retrogressive overprinting. And this was mapped in some detail by Mark Heiter, 1 to 25,000 scale in the mid 2000s, a really beautiful map that he did of the whole island. But we've gone in and mapped it in a lot more detail for the purpose of identifying sort of individual faults that are present here, as well as kind of collecting information on the length scales and types of heterogeneities from a rheological perspective. So I'll walk you through our general workflow for studying this region, especially aimed at those who maybe aren't field geologists. So first, we simply map the rock units. In this case, we're mapping at really high resolution, 1 to 5,000 scale. We have sufficient exposure generally to do this. We do this using boots on the ground and also by sea. We take some pack rafts around. It's very, very pleasant to hang out on the Mediterranean in these little inflatable rubber duckies. And this locality has a really wide range of rock types, so there's a lot of detail needed to really capture what's there. There's marbles, there's serpentinites, there's mafic gabbros, metasedimentary schists, basalts, metatufts, all sorts of things. And these represent the disaggregation on the deep interface of this ocean basin. Secondly, we also look really closely at strain distributions because this is what can help us identify paleo-subduction thrusts that we think are responsible for the progressive underplating of this subducted ocean basin. And we're really fortunate to have these really nice strain markers in this region. For example, on the left here, this is an igneous breccia, which represents a magma mingling texture where both felsic and mafic magmas are kind of blobbing together in the original oceanic crustal setting, and they form these sort of non-immiscible clasts. And now they're subducted, and they essentially start to disaggregate and form sort of lenses that get smeared out. Eventually, they become sort of banded gneisses, and in some places, they become very smeared out and myelinitic, like on this image on the right. So these strain markers are really useful in allowing us to locate the highest strain zones in the field area and infer the position of kind of the paleo-subduction thrusts that, like I said, are responsible for the assembly of this subduction complex. So here's a map of kind of where the strain distribution or most strain is, and then we use the strain distributions and the juxtapositions of different rock types from the first two steps to define the main thrust faults that are showing up in this belt. And then lastly, we just restored displacement on the late cross-cutting faults that post-dated the main subduction so that we can get a kind of coherent representation of the original subduction interface configuration. So this gives us a kind of snapshot of the subduction interface at near peak conditions, the conditions that we think correspond to the slow sub source. And we interpret each of these thrust faults that from north to south as representing a paleo-subduction thrust that accommodated progressive underplating through time. So the slab would have started out here in accreted material and then progressively stepped down. And each of these is a paleo thrust, probably developed over a few million year timescales. So now we can use this kind of workflow to say something about these questions that we have. So starting first with our questions of the types and length scales of heterogeneities. So one of the first ways that we try to understand heterogeneity as structural geologists is just by looking at basic field relationships. And there are features that structural geologists have worked on for nearly a century that provide useful qualitative clues regarding rheological contrasts. For example, Boudin matrix relationships, where the sort of sharper the corners and the less lensoidal the Boudins, the more viscosity or rigidity contrast you expect across the materials. Similarly, fold wavelengths, the wavelength and amplitude of the folds and multi-layers tell you something about the rigidity or viscosity contrast across the layers. So this is one tool that even though it's classical, I don't want to ignore because it's something we use to build a lot of intuition about rheological contrast just by looking in the field. And when we apply these kind of qualitative tools, we find that not only on Syros, but pretty much all over every subduction complex in the world, many deep subduction shear zones, there's this very common relationship where the most prominent heterogeneities nearly always involve juxtaposition of mafic oceanic crust and ultramafic mantle and sedimentary protoliths. This produces heterogeneity for two reasons. Firstly, there's a primary contrast that mafic oceanic crust is just inherently strong. And then there's a secondary effect that relates to the fact that contacts between mafic and ultramafic rocks and metasediments commonly produces metasomatism and fluid rock interaction. And this tends to produce much weaker, commonly phyllosilicate-rich metasomatic zones. So this is just shown kind of schematically in this sketch of potentially underplated fragments of oceanic crust we might see as kind of brittly fractured and boudinaged, and you've got this metasedimentary schist flowing around it. And then across the contact, you start to get fluid rock exchange, and you might expect a metasomatic sort of halo that is similarly weak. So you can produce even more weak material than is already there through the fluid rock interactions. So to show you some of these examples of these from Syros, here's one of my favorites that I show in basically every talk I ever give. It's an example from Southeast Syros that nicely shows this eclogite facies sort of mafic pod. It's kind of lensoidal, so you might assign it to this kind of level of qualitative contrast of level B here. And it's embedded in a blue schist facies metavolcanic and metasedimentary matrix. Here's another example from the compost belt with this eclogite lens kind of embedded in a marble and metasedimentary schist matrix. You can see how the metasedimentary foliation wraps around it and encases that brittle lens, and the mafic block is kind of brittly dismembered within it. And then this second example of fluid-related metasomatism forming rheological heterogeneity along the boundary between sediments and mafic rocks is also common and especially well developed in the compost area. So here's an example of a localized shear zone and with metasedimentary schists on the right side, and then metasomatic shear zone in the greenish colors on the left. And the matrix of this shear zone consists of chlorite, tremolite schist with some layers of talc schist as well. And then you can see embedded within it are these strong lenses of blue schist facies, gabbro, sort of dismembered and strung out as semi-rounded blocks and boudins. So the rock record gives us a lot of clues as to rheological contrast. But in addition to these qualitative observations we can make in the field, we can actually also use quantitative data and rock physical properties derived from lab experiments to look at heterogeneity in a much more quantitative way. And this is only made possible thanks to many of you actually who are sitting in the audience, because there's been this really large effort from the experimental community to better characterize subduction metamorphic materials just over the past 5 to 10 years. And so as part of this study, we've been compiling, and in some cases collected ourselves, data for these sort of 4 key properties for the rock types on Syros. So permeability, viscosity, friction coefficient, and rate and state friction parameters. And I'll walk you through the compilation. It includes many, many references, so you'll see lots of text. Sorry about that, but I'll just highlight some of the key points since it's really a lot of information. But here, for example, it's a compilation of permeability in subduction, sort of deep subduction conditions from a range of different experimental studies. And I'm showing the whole range of every study that we could find. And then the pink are representing, the dark pink is perpendicular to foliation, and the light pink is parallel to it. And the main thing to recognize here is that we have what we expect is that gabbros and eclogites, these coarse-grained, sort of strong igneous origin rocks or protolith rocks, are very low permeability, and then you start to get higher permeability values when you reach the phyllosilicates, but still generally all very low. And then in terms of viscosity, this shows something that matches very well with what we expect from our qualitative observations in the field, that metasediments and phyllosilicate-rich rocks are all down here at this kind of 10 to the 19 viscosity for typical subduction strain rates, whereas blue schist and eclogite show 1 to 3 orders of magnitude higher viscosities. And then if we look at friction coefficient, also some pretty intuitive results here from this compilation. So things like gabbros are the strongest. They tend to follow kind of Byerlee's law. But then you get down to the phyllosilicates and you have extremely low coefficient of friction measured for those. And then in terms of A minus B, or velocity weakening versus strengthening, the take home here is that only the sort of relatively high frictional strength rocks like the blue schist and gabbros show velocity weakening behavior, whereas all the rest are velocity weakening or neutral on average based on the compilation of various studies. So then to actually use these data in a quantitative way, once we have this restored map with what we interpret to have been these sort of megathrust segments progressively in place through time, now we can start to examine both along and across strike fault heterogeneity on each of these structures. And I think what's cool about this is we're really trying to do this at the kilometric length scale rather than just single outcrops. There's often a kind of disconnect of geologists trying to upscale to at least the minimum length scale of resolution of geophysical data. And I think a place like Syros, where you have nearly 100% exposure and you have 5 or 6 kilometers of exposure, allows you to start to bridge that scale gap. Here I'm plotting the rock types. So I've just taken each fault and kind of stretched it out into an along strike line. And I'm plotting the rock types as a function of distance along each fault, with the top part representing the hanging wall and then the bottom part representing the footwall. So that's the fault 1, for example, is just this fault stretched out into a single line of function of distance along strike. So once we have all the rock type distributions, then we can kind of repopulate this with the properties that we compiled. So for example, here's permeability as a function of fault distance along each structure. Here's viscosity as a function of fault distance along each fault. Here's coefficient of friction, and here's the velocity weakening versus strengthening patches. We can also look at contrasts from hanging wall to footwall, which can be, in the case of a thrust fault, can be quite relevant to, for example, whether you can store fluid pressures. And these are kind of busy diagrams, so I'm just showing them for one of the faults, but you can basically divide one side of the fault by the other to look at how much each of these properties varies across the structure. So once we have these variations in fault properties, then we can kind of analyze them in a similar way to analyzing fault roughness. But in our case, we're applying it at the meter to kilometric length scale rather than sort of micro or nanoscale, as is often done with roughness kind of studies. So we could look at things like the frequency of different heterogeneity types, the area fractions of each heterogeneity type, the maximum heterogeneity type sort of consecutive patch size, the distributions of the patches, are they clustered or distributed, the fractal dimensions of different patch sizes, and the co-occurrences of these different heterogeneity types. And we're doing all of this. We have kind of plots for all of this, but I won't show each of them, just show some of the key ones just in the interest of time. But for example, here's a histogram of the total number of these heterogeneities on all of the faults. So you can see that viscosity contrasts and friction contrasts are the most abundant, just in terms of raw numbers. But then if we plot them as a function of total fault length, then we see that velocity weakening patches and viscosity contrasts show up as the more prominent features. They're up to about 33% or so on average of each fault. Here I'm plotting just the size of each heterogeneity against the area of the fault that it occupies. And I think what's interesting about this plot is, even though we have up to 5 kilometers of fault exposure, and we still find that the individual heterogeneous patches are never larger than about 1.4 kilometers. So we never get these heterogeneities spreading all the way across the full length of the fault. So we seem to have a length scale cap of about 1 to 1.5 kilometers or so. Similarly, if we look at just velocity weakening segments, we find that they generally fall at a sort of fraction of each fault of about 0.4. So meaning only about 40% of each of these structures has velocity weakening material along it. And I thought this was interesting because there was some work that Rob Scarbeck had done trying to analyze the relevance of frictional heterogeneity and contributing to slow slip. And he had this plot where he was showing velocity weakening fraction, so just like percent of velocity weakening material on a structure, this eta term here on the x-axis, against A divided by B for the velocity weakening material on the y-axis. And the gray zones shows this kind of middle area where his models were able to produce slow slip. And if we look at kind of, it's just roughly, the uncertainties are a bit large here, but about 40%, our 40% area fraction of velocity weakening material, with our A minus B values for the gabbros and blue schist kind of roughly overlaps with his gray zone. So this might say we have the distribution of velocity weakening material is just in that sweet spot that we might produce slow slip. So
Whitney, sorry, it's kind of,
yeah.
I wonder if this is a good time to just clarify. So when you think about these patches and look at them in the field, do you think of them mostly as kind of original heterogeneity in the source rock, or are they some kind of like a fracture? How are the patches originally made, let's say?
Yeah, so they're original heterogeneity that gets progressively disaggregated through strain. But yes, they are all of these are corresponding to original heterogeneous rock types in our case, sometimes formed later through metasomatism, right? So maybe not always the protolith, but they certainly relate to pre-existing heterogeneity.
Gotcha. Thank you.
And so kind of the idea is to see like, well, does that evolve, that pre-existing heterogeneity kind of evolve to some characteristic length scale, right? And or is it just, random based on what was subducted?
I see. Okay. Yeah, thanks.
Okay, so just kind of summarize this question about the types and length scales. We see these velocity weakening patches and viscosity contrasts are the most common kind of types of heterogeneities in this zone, but the maximum length scales seem to be limited to about 1.5 kilometers or less. And then the velocity weakening material distribution is around 40% on average. Okay, but then we have these large and small scale heterogeneities, but maybe this also gets at Chris's question. Next, we want to ask whether there's evidence that these heterogeneities actually did host some form of transient deformation that we can argue likely occurred over faster timescales than background aseismic creep. And this is really, I think, the trickiest thing for us as geologists in subduction complexes, because nearly all of them subducted to these sort of blue schist and eclogite facies conditions, that's many, many kilometers of depth. They have some background deformation that's largely homogeneous and ductile and viscous. It's very common, for example, to see multiple generations of ductile folds, as in the left photo here, or as in the myelinite photo that I showed before, where you've just completely homogeneously strained the rocks to form this really uniform foliation. That said, though, despite this pervasive sort of background evidence for viscous creep, it's also really common to find evidence for coeval, brittle, or localized deformation. And we distinguish sort of two forms of these, even though they often occur together. So one is this cyclical brittle dilational and dilational shear slip that's very common in or around the margins of the mafic lenses here in Syros. The other is localized slip on phyllosilicate layers or shear bands, commonly also accompanied by veins that appear simultaneous or coeval. So just to show some examples, coming back again to my favorite eclogite Boudin, this one is riddled with abundant veins within it. So this is telling you had some brittle cracking event sort of breaking up this mafic eclogite here, but also along its flank in the background, there's this evidence of vein emplacement during progressive ductile rotation. So this is showing veins in place at a high angle to the foliation and then gradually rotating with time through subsequent ductile strain. Similarly, there's also evidence that this outcrop was sort of simultaneous rather than alternating frictional viscous deformation. So this image shows these brittle dilational shear fractures developed in the rigid eclogites, and then they kind of soul outward into the surrounding weaker matrix in the form of much more distributed viscous deformation. We can also see these kinds of mutual cross-cutting relationships between slip on phyllosilicate-rich shear bands in the metasomatic zones and vein emplacement. So here's an example of a metasomatized blue schist with many generations of veins. You can see all these white sort of resistant layers of quartz and mica sticking out here. Some of these veins are parallel to sort of C-type shear bands that are cutting the foliation. Others are, S-type shear bands that are cutting the foliation, and others represent sort of higher strain shear bands where the veins have rotated parallel to the foliation. So multiple generations of vein emplacement is interpreted from an image like this. We can also see similar features if we come back to this example of chlorite tremolite talc schist I showed earlier. So some veins in this foliation are transposed parallel to it. So you can see all these white layers in here. Some are forming sort of moderate angles and only partially cross-cutting, and then some are cutting at a really high angle. So this suggests you have multiple generations of vein emplacement during foliation development. Additionally, at the microscale, it's very common to find evidence for craxial textures that support the notion of multiple incrementally opening events over time, brittle cracking events. And they often preserve very high pressure minerals, so we know that this is occurring during the prograde stage as opposed to later. So although we can't trace a single surface for the kilometric length scale of a slow slip event, we do see a lot of evidence for transient sort of brittle deformation embedded or encoded in even these dominantly ductile rocks. And it's prominently in the form of cyclical dilational shear slip and veining. And others who have studied these kinds of outcrops, like Aki Fagrain, I saw he gave a talk a few weeks ago in this session, and have observed very similar features. So to come to the last question on fluid pathways and permeability, the primary fluid conduits that we see on Syros are actually features I've already highlighted in some of the earlier discussion. So the plumbing systems in subduction zones, this is not a new concept. Lots of people have recognized that they tend to consist of two primary fluid conduits. There's these sort of metasomatic fronts that form parallel to the foliation. And then there's cross-cutting transient fractures or veins, like I was showing in the previous images. And here's an outcrop that nicely illustrates sort of both of these features, but these kinds of things are observed all over Syros and many other subduction complexes. So this is an image of a drone model of an outcrop. It's about 100 meters across here. And I'll just walk you through some of the different features that we see here and how we interpret them. So firstly, one of the main things that stands out is the main fabric. This pervasive foliation. It's defined by sort of banding and transposed layering. We interpret this to represent bulk viscous deformation along the subduction interface shear zone. So developing over relatively slow background aseismic strain rates. But superimposed on top of the foliation, we can see some features that relate to fluid flow. So firstly, we see these really more brighter blue-green bands that I've labeled here with the blue hours. There's this sort of pistachio green, and then there's this blue-green. And these we interpret as representing sort of metasomatic fronts that are traveling parallel to the foliation and kind of altering the rock. We look up close at them, they look like this. There's this gradational contact between the host green schist, and then it grades into essentially a chloritite, which has to be a metasomatic rock, and suggests, metasomatic origin. And then lastly, another form of sort of fluid conduit that we see is superimposed on both the foliation and the metasomatic zones. We see this abundance of dilational and dilational shear faults, Boudin necks, filled and shear bands that all have quartz epidote and calcite precipitated in them. And so the way that we kind of interpret this is something like this sketch, where the foliation and the foliation parallel fluid conduits are sort of transiently cross-cut by high angle fractures, representing a sort of breaching of this system and a much more transient state permeability. The veins eventually close and then start to become sort of deformed and smeared again by viscous creep in the interseismic periods until the fluid pressures kind of build up again to produce a new set of fractures that cross-cut everything. And this can continue over very long timescales. So these features kind of potentially resemble a sort of fault valving type mechanism, similar to what several people have interpreted for geophysical data in modern subduction zones. So we wanted to see if we could understand the permeabilities associated with these two forms of fluid conduits, the metasomatic zones parallel to foliation and the cross-cutting fracture systems. First, if we consider the metasomatic chlorite layers, these by definition represent diffusional or porous flow, so it's kind of flowing along grain boundaries. And there's a nice set of experiments by Ganshorn and others that specifically measured diffusional flow in chloritite, this exact rock. And they find this process is extremely low, suggesting suggesting very low permeabilities, less than about 10 to the 21 meters squared. So if anything, these metasomatic zones likely represent permeability barriers at the time scale of slow slip, and the permeability associated with that sort of porous flow or diffusional flow is way too slow to match something like tremor migration patterns. So we know that these kind of metasomatic fronts can't be something that could be responsible, for example, for tremor migration. By contrast now, if we turn to look at the cross-cutting fracture systems, we've also tried to roughly quantify permeability in these using some key assumptions that I'll discuss in a moment. But in terms of methods, we first sort of mapped the last generation of cross-cutting veins in this area. Then we use this nice software from Healy and others called FracPack that allows us to make 2D permeability estimates from the mapped fracture pattern. And this software requires an estimate of the fracture aperture, which we assumed could be approximated by the width of crack seal increments measured in thin section. Another assumption we had to make here was that the veins we used in the permeability calculation represent a sort of interconnected network that opens simultaneously and in very close succession. And this is consistent, though, with observations of sort of mutual cross-cutting relationships and evidence for high fluid pressures and low differential stresses in these kinds of environments. There's more kind of detail on our assumptions and such in this paper by Jesus, one of my postdocs that we published in GeoL in 2023. Either way, our assumptions lead to us having a permeability estimate that is really a maximum, the highest we could possibly get it from this fracture network. This approach led to a permeability estimate of between 10 to the minus 14 to 10 to the minus 15 with higher values, slightly higher values across dip than a long dip. And the kind of uncertainty represents uncertainty in the aperture width in the crack seal textures that we saw. So we kind of used a range from epidote and quartz. So the take-home messages of this kind of permeability part are firstly that these estimates of the kind of fluid flow that you can expect through permeable fracture networks gets much closer to the tremor migration rates estimated from diffusivity based on tremor migration. If you consider the uncertainties, we're a couple orders of magnitude off, but if you consider the uncertainties, maybe you could call them compatible. Kind of depends on how robust you think either of these estimates are. Secondly, though, either way, this plot on the right is trying to demonstrate that the change in permeability from background to transient fracture controlled seems to end up about 6 orders of magnitude. So this is really huge changes in permeability happening relatively suddenly. So this has important implications for models of fluid-driven transient slip events. And then the last take home is just that this is just one sort of decameter scale measurement for the deep interface, but we can do the same kind of workflow or apply the same workflow to other areas with similar large scale contexts so that we can see how representative these values actually are. So to kind of summarize the view from geology, there's lots of features that match interpretations from geophysical observations. So we see these heterogeneities. They arise due to sort of deep underplating of mafic oceanic crustal fragments and metasedimentary slivers and the kind of juxtaposition between the two. They seem, by the time they get to the deep interface representative of the deep slow slip source, they seem to be sort of kilometer in scale. Which may mean that they can scale well with tremor sources. Then we do see evidence for transient slip recorded by brittle dilational shear veins and slip surfaces and phyllosilicates. We don't see these actually linking up. I'll come back to this in a moment as one of the key questions, how these actually scale up and link to form slow slip surfaces. And then we see evidence for fluid flow in the form of both diffusional zones parallel to the foliation, but those we think have to form over really long time scales. But transient fracture networks that develop both along and across dip could potentially develop on timescales relevant to SST. So there are several apparent agreements between what we see in the geology and then the inferences from geophysical monitoring. But there are still a couple of key open questions, or many open questions, but a couple of which I'll just finish off my talk by highlighting and see if anyone has thoughts or ideas. So the first one relates to how the kilometer scale heterogeneities that we see in the field that seem to characterize maybe this minimum scale of tremor sources. how they can actually link up to produce the spatial dimension of slow slip, which is on the order of tens to hundreds of kilometers. And one option that Tara Scary and I explored using numerical models was this possibility that transient sort of discrete frictional slip events can nucleate in rigid class, say a mafic oceanic lens of a kilometer scale, and then can propagate through the viscous matrix, except that depending on the viscosity of the matrix in between, you can kind of slow ruptures down and cause them to kind of damp slip, very similar to what you would do if you embedded velocity strengthening material in that. And in cases where, for example, the matrix viscosity was too high, we would expect ruptures to accelerate through the shear zone to produce fast earthquake-like velocities. Whereas if the matrix viscosity was too low, the ruptures would leave the class and then just entirely quench in the matrix. And this particular model is kind of showing an example where the viscosity is kind of in this sweet spot where it produces some velocity strengthening type behavior, so it slows the ruptures down, but they can still propagate through the whole model domain, but they do so generally at relatively low slip rates. So you can see many of these have actually gone from class to class. They start in a class, they then propagate through the matrix, slow down, then hit another class and speed up and slow down. And that's what kind of these ruptures are doing here. They're propagating all the way through, but it's slip rates of about 10 to the minus 6 meters per second. And we use this to kind of produce a little regime diagram where if you have the matrix viscosity, or it shows the types of events we expect for different values of matrix viscosity and then class concentration. And this indicated that large scale slow slip should occur for viscosity values that are intermediate. So basically close to the brittle ductile transition of whatever material the matrix consists of. And the viscosity window where slow slip is expected tends to widen for class densities that are higher, since it sets up overall higher stresses in the shear zone between the class. So this is just one possible way that we could perhaps envision heterogeneities linking up. Another explanation that maybe Aki Fagereng talked to you all about a few weeks ago, that his former postdoc Adam Behl proposes this idea that in cases of high class densities, the class themselves may occasionally end up close enough to interact and produce force change that temporarily jam the subduction shear zone and then induce a sort of brittle stick slip type behavior along the length of the shear zone that could also potentially scale with slow slip. And these authors similarly looked at kind of class densities and matrix viscosities that are needed to promote this kind of jamming process. And then the last question I'll highlight just relates to something I briefly mentioned earlier, which is how the transient deformation features we observe in the field should scale to low frequency earthquakes or episodic tremor slip events in time. And we can't really assess slip rate on individual structures in the rock record, besides to say that they either formed faster than steady state creep or slower. But we can at least consider that one of the primary rate limiting components in these frictional viscous systems should be the rates of mineral growth in veins. So there's some potential for correlation between recurrence intervals and low frequency earthquakes or slow slip to the process, the kinetics of vein precipitation and healing. And this has been looked at for minerals like quartz, both theoretically and experimentally. But unfortunately, I think there's just really large uncertainties depending on what kind of method is used. For example, this plot in the middle shows a suite of laboratory experiments on quartz conducted many years ago by Susan Brantley and others at 400 to 500 degrees C. The x-axis is showing time, and then the y-axis shows regression distance in microns, which you can think of as equivalent to sort of precipitation. And this plot is showing vein precipitation of several microns on timescales of only a few hours for this temperature range. So you can grow this quartz and seal the structure really rapidly. And so this would suggest that vein healing could potentially match the timescales of low frequency earthquake recurrence intervals, for example. But then on the right, I'm showing a plot that Don Fisher, from a paper Don Fisher published a few years ago, in which they used a more kind of theoretically derived kinetic model with different rate controlling mechanisms to infer sealing times, and plotted up those times for typical subduction geotherms, Cascadia being the warm case and Honshu being the cold case. But even for quite warm subduction zones like Cascadia, the maximum sealing times that they get are on the order of 10 to 100 years. So much too long to match either LFE or slow slip recurrence, maybe more consistent with regular megathrust earthquakes recurrence interval. So the take home here is just that our constraints on vein sealing and healing sort of span many orders of magnitude. And we therefore don't really understand the extent to which they might control recurrence intervals in these transient types of events. So with that, I think I'll end here and leave my conclusions for people to read, and then I'm happy to take questions. Thanks so much for your attention. Sorry, that was a little long.
No, perfect. Whitney, thank you very much. Really a fabulous talk. And I'll invite people to unmute or turn their camera on and join me in thanking Whitney for a great talk. Lots of interesting stuff, lots of different directions, and really, really nicely summarized. So, well, we give Whitney a chance to catch her breath. Best way to operate is to use the raise hand feature, put ourselves in line, and it looks like this. Yeah, go ahead and join the discussion. Think of some points of clarification, questions, of course, things like that. And while you were all thinking about what your question might be, I would like to start with one. So, when we think about this, when we think about the cross-cutting relationships that you showed us in a few places, and you said they were gonna, they were seal breaching transient events. Whitney, now, like, how big can those be and still produce LFE instead of a real earthquake? You know what I mean? Like, there must be some like level of localization that you see in those seal breaching events that's too localized, too narrow, too brittle to produce an LFE. It should produce a real earthquake. Is that
Well, so these results would argue that it becomes an LFE because the size of the original thing that can break brittlely is too small, right? So you try to propagate outside of these heterogeneities, right? These clasts or these big kilometer scale rigid blocks, and you can't. And if you could, you would become a regular earthquake. So you're nucleating, the reason you're an LFE is because you're limited by the size of your little asperity. And so